just leave it as it is. Sometimes it works as well. Okay, we'll see an example like that. So then it's not working again. Okay, then use the last piece, that is delta S by delta BQK equals to negative PK to find the solution to the equation of motion. Solution to the motion. So as you can see, Hamiltonian particularly, and most specifically Hamilton-Jacobi theory, it helps us solving the differential equation. That's where the beauty lies, beauty of this Hamilton-Jacobi lies. So other methods like Lagrangian or Newtonian, they never helped us solving the differential equation itself. So do you have any question? And do you have a clear difference between these four formalisms? Advantages or disadvantages? So like more sophisticated formalism you have, the more difficult it to perform. So Hamilton-Jacobi is the most sophisticated one, but when it works way better than the others. I think it helps, right? Do you have any question so far? Hello? We have to solve another problem. So
yeah, we can go ahead.
I have a question which is not maybe related to the upcoming math. Okay. I found in the internet that the standard model has been written in Lagrangian form. Okay. So is this the most important reason that Hamiltonian-Jacobi model is too much difficult to solve mathematically, and that is why they have constructed the equation with Lagrangian?
No. Like in field theory, they actually try to stick with the most convenient one. So Lagrangian is basically the most convenient one that you can write down the equation of motion. So probably for many field theory cases, you do not have Hamilton-Jacobi theory itself. Solving is a far cry thing. We are not even talking about that. So
is this because of the difficulty of mathematical problem?
Yes, that's one thing. Also, many times they are not interested in solving the differential equation itself. So they can just go into a computer and code it, and they find the solution. So why do you care?
Okay.
And for particle physics, they actually try to stick with the simplest mathematics, but here we are like GR people of the guy. They try to dive into the most sophisticated mathematics. So for our case, we actually like this kind of theories. The more sophisticated it is, the more we like, the more we love actually.
Whatever.
Is there any other question? So actually we have a particle physicist among us, so you could ask this kind of question to him as well. You want to add anything, Carl?
Don't expect any answers. I'm still mired down in figuring out what neutrinos are. So.
Okay. So we can at least do the harmonic oscillator problem, because in a physics class with a physical theory, if you do not do harmonic oscillator, then it's not a good thing, right? Like, if you are a physicist, you must try to solve harmonic oscillator with your theory. So let's, we do not have that much time, so I can do either one, like either harmonic oscillator or pendulum problem. Which one do you want me to do?
Harmonic oscillator.
Harmonic oscillator? Okay. So we have to start with, for harmonic oscillator, to solve with Hamilton-Jacobi theory. Oops, I want to write harmonic oscillator. Harmonic. I have to go back to 100%. Oops. Okay. Harmonic oscillator. So if you want to do with Hamilton-Jacobi theory, what is the first step you do? To set up a coordinate. Which coordinate you want to do with your harmonic oscillator? 1D harmonic oscillator?
X.
Cartesian-like coordinate, right?
Yeah.
So X. Okay. So now write down the Hamiltonian. What's the Hamiltonian of the system? Hamiltonian of a harmonic oscillator. It's 1 over
Square
twice
by 2m.
p squared plus half kx squared.
Yeah.
So now we need to substitute the definition of moment. So that is, definition of moment is P equals to delta S by delta X. And write down the Hamilton-Jacobi equation. So using that thing, we have 1 over twice m delta S by delta X whole squared plus half kx squared. This is the Hamiltonian, right? Plus delta S by delta T equals to 0.
Yeah. Can you use separable of variable technique here? Separation of variable.
Separation of variable, what? You have to do that.
Like x is equal to something function of x into something function of t.
Yes, we need to do that. That's the next step, right? That's our answers.
Well, it can be multiplication. What I wanted to say.
Yeah, it could be, but let's see if it works.
Okay.
It could be, but finding that kind of multiplicative thing is much more difficult in Hamilton-Jacobi theory. So you are lucky that we do not need to consult that kind of answers here. So you can try it by substituting that kind of product things, like try this thing, S x of t.
And there is some problem because the del S del x term is square and del S del t is there is no.
Try this. Let's see what happens. Okay. So if you substitute that, then delta S over delta x, basically dsx over dx. Also delta S over delta t equals to dst over dt due to our answers. So substitute that, we get 1 over twice m dsx over dx whole squared plus half kx squared plus dst over dt equals to 0. Now what can we conclude from this relation?
dst dt equal
to be constant, right?
Yes.
Because the other part is only function of x, it doesn't have any t.
Yes.
So if this function depends on, this part depends on time, then this part has to depend on time, and that's not true as well. So the only possibility is that dst over dt, this has to be some constant, let's say
minus
negative.
e. Sorry, minus e just.
Yeah, so integrating this thing, it gives us st equals to negativity.
Yeah.
and substitute that E over there, E over that equation, we get 1 over twice m dsx over dx whole squared plus half kx squared equals to E, right? I switch the side.
Yes.
So it gives us dsx over dx whole squared equals to twice me minus km x squared, right? Doing the
Yes.
algebra.
Yeah. Yes,
So
right.
we have our dsx over dx equals to square root of twice me minus mk x squared. So integrating that thing, why isn't it working? Okay, integrating this thing, it gives us sx equals to integration square root of twice me minus mk x squared dx. Now tell me, what do you do? What do we
Now we will just factor out 2me
So
terms.
you want to perform the integration, right? You want to perform the integration.
Yes.
I am saying that you need not to. So as I said, you may not need to integrate itself. Most time you do not need to, at least at this stage. You will need later. So recollecting the s, so we get s equals to negative et plus sx is integration of this whole thing. You'll see why we do not need that. We need to integrate it explicitly. Now we have just one coordinate, right? X coordinate. So our s is, it must be dependent on x and a constant, some q, we do not know which one that, and also t. So we can see x and t over there. Which one is our constant q?
E.
It's E.
Yes.
This is E, right? That's the separation constant, we call it. So now the final piece is delta s over delta that constant equals to negative of another constant. Tell me something. Give me some constant.
Alpha.
Alpha, big alpha.
Okay.
Okay. So that gives us, take derivative. So the first part gives you negative t, right?
Yes.
And the second piece, actually you can perform the differentiation under integration. That is integration delta delta e of this whole thing. You can do that.
Yes.
So simplifying this thing, we get t minus alpha equals to integration. If you take derivative, what do you get? So there will be a power like that, then square root of twice me minus mkx squared, and then you get
Twice m.
m. Is that correct?
Yes.
So that's nothing but you can actually factor out. You can factor out, like these two cancel out, and you can factor out square root 2me out of this integration. So you can write integration actually out of the integration, that's what I mean. So m divided by square root of 2me, that's what I want to write. Integration 1 by square root of 1 minus What do you get here from the algebra?
K by 2e.
K by 2e. Right. K by 2e into x squared dx. So, are you able to perform this integration?
Yes.
So, what do you do here to perform this integration? Let's substitute k, this thing. Let's substitute this thing. We can do that, right?
Yeah.
So that gives us, by that substitution, we get t minus alpha equals to integration. Sorry, not integration. There are some other stuff as well. M by square root 2me integration, then 1 by square root of 1 minus u square. And then what is dx? Dx equals to du multiplied by square root 2e by k, right? Is that correct?
Yes.
Okay, now you're almost done. So what we can do is
root over m by k.
So this thing and that part cancel out. So we have square root of m by k, is it? Or
Yes, m by k.
yeah, it's m by k, right? So, and then what is the integration of
Sine
this
inverse
thing?
u.
Yes, this is sine inverse u.
Yeah.
So instead of u, we need to substitute this thing. So what do we get? Root k by 2e into x. This is our t minus alpha. So inverting this thing, we get square root k by m into t minus square root k by m into a, and sine of this thing equals to square root k by 2e into x. So we found our solution like this. Why isn't it working? Okay, so we end up having x of t equals to x naught sine of square root k by m into t minus delta, where our x naught is square root 2e by k, and my definition of delta is square root k by m into a, that alpha, right? So this is the solution to harmonic oscillator, a general solution, and you can substitute the initial data to find like a specific phase phase angle and like the specific amplitude x naught. We haven't substituted the initial data yet. Okay, so what have we learned today? Hello?
Yes, Hamilton-Jacobi equation.
So how to use Hamilton-Jacobi theory to integrate something? Hamilton-Jacobi theory, it helps us directly integrate something whenever you have a procedure that can separate your an answer that can separate your S, like Hamilton-Jacobi equation, then you are almost done actually. That automatically integrates half of that thing, and you're left with the other half that you need to integrate explicitly.
Yeah, and Hamilton-Jacobi equation is also like Schrodinger equation type thing, I think. Though there is no imaginary part, but there is a first order derivative of time and second order derivative of no, second order derivative is not here, but there is a similarity because
No, there is. That is inside of your Hamiltonian actually. You are talking about a specific Hamiltonian system that has like p square by twice m format.
yeah.
That it is there.
Yeah, and in case of operator, it turns out to be Schrodinger equation.
Actually, we have 10 more minutes. We can see how we can have our Schrodinger equation out of this. So, say you have a one-dimensional system. Your Hamiltonian must have a format 1 over twice m p square plus potential of x, like that. So your Hamilton-Jacobi equation would be 1 over twice m p squared plus v of x plus delta s by delta t equals to 0.
Yeah.
So now, substitute this thing. S equals to some constant that you need to find. What's that? K multiplied by log psi. And substitute it over here. So if you do that, you get 1 over twice m p square plus v of x plus k 1 over psi delta psi by delta t.
Yes.
So multiply your psi through to this equation, and it's a super heuristic proof. There are actually more rigorous version of this, and that actually requires some part of the like field theoretic approach as well. So I'm not going into that, but this is at least the basic you need to know. So k is some experimental constant that you need to set, and it turns out that this k has to be like IH cut or negative IH cut.
Yeah.
Also, so it gives you like IH cut delta s by delta psi by delta t. Also remember your P has a definition in Hamilton-Jacobi delta s by delta x. Use that. So you get P equals to k 1 over psi delta psi by delta x. So it gives you P psi equals to k delta psi by delta x. So now substitute your definition of k, you get P psi equals to negative IH cut delta psi by delta x.
Yes, this is nice.
Yeah, so Hamilton, Schrodinger equation actually in his original paper, like it's available on the internet, or also that in the group we added you, that you can find that original paper of Schrodinger, and his original derivation was it started from Hamilton-Jacobi, and like we call it quantization, first quantization, but the idea is like he imposes that psi has to be something like wave as well, so that automatically gives rise to
well, there is two things to notice. Firstly, the thing is that he wrote that k is equal to IH cut, and I don't know how he could imagine that. Yes, psi is necessarily complex, so he can impose this condition.
No, there are reasons. That's kind of straightforward, because if you start with Schrodinger equation, and if you claim that your psi is real, and
psi is necessarily complex. If psi is not complex, then the vector space is not complex, and there are many theories of linear algebra which only applicable for complex vector field only.
So actually, yeah. So you're talking the same thing in a really complicated way. So the simpler way is to just start with the assumption that your psi is real, and I try to find the solution for just a single free particle, and you'll end up having a purely imaginary wave function for your free particle. So it it violates your initial assumption. Do the opposite. You consider it purely imaginary and you'll have a real one. So the only possibility that you can reconcile these two things is considering psi as complex, and we'll leave as k this constant k as our experimental constant that we need to find from experiment. So it has to be complex when you do that thing, like just apply this thing for hydrogen atom. You'll see that it has to be complex to find something real out of it. So it's a kind of a straightforward thing. People do not talk that much about, but it's really interesting to know. So basically, quantum mechanics has two standard formalism: Schrodinger's formalism or wave mechanics formalism, and another is matrix mechanics formalism. Basically, Hamiltonian dynamics automatically gives rise to matrix mechanics, and Hamiltonian automatically gives rise to Schrodinger equation. Like classical counterpart is this: delta S by delta T plus together with delta S by delta X equals to P. It automatically gives rise to like H psi, as you have seen already. Delta. Is the equation. Actually, I'd write like this: IH cut delta psi by delta T equals to 0, and also delta psi by delta X equals to negative IH cut P psi. This is one thing. This is the corresponding between this Hamilton-Jacobi theory and wave mechanics, and there is a correspondence between the matrix mechanics as well. That is in Poisson bracket formalism, the same thing like we write for
commutator.
Yeah, for any variable f, if you take derivative of that, that is a function of phase space q, p, and t. You can actually prove that. So it gives you delta f by delta q dot plus delta f by delta p dot plus delta f by delta t.
Yeah.
So using Hamilton's equation, q dot is basically delta f by delta q, and q dot is delta h by delta p, plus delta f by delta p dot is negative delta h by delta q. So we can write, it's an antisymmetric form, that delta f by delta q delta h by delta p minus delta f by delta p delta h by delta q plus delta f. So this thing we have written here, it's called the Poisson bracket of f and h. So classically it's written as this thing, Poisson bracket of this thing. So this is basically the Hamilton's equation, nothing else. F dot equals to this thing. So the quantum counterpart is the same thing, just replace this
with commutator.
That's, yeah, you get 1 over IH cut, then FH. So these are the like Hamiltonian dynamics is the corresponding like it has the correspondence with matrix mechanics and so on. Like as I said, Hamilton-Jacobi has the correspondence with wave mechanics.
Yeah.
Okay, is there any other question? I think I have utilized the whole time so far.
So similarly, we can solve the pendulum for the pendulum also, right?
Mm-hmm.
So for that, we have to consider the polar coordinates, right?
Yes.
Okay.
You start with a polar coordinate like this. Let's write it down then. So your Hamiltonian would be 1 over 2m.
Yeah.
Then what?
P phi square.
P phi square.
In denominator L square.
L square. Yes.
Minus mgl cos phi.
Is it minus or plus?
It's minus.
It's minus. Okay. Minus mgl cosine phi. Yeah, start with that. And also for Hamilton-Jacobi equation, like 1/2 m L square delta s by delta phi, because that's the conjugate one, right?
Yeah.
And then start separating and we'll see what happens.
Yeah, I'll
It's
try
the
this.
integral solution that we got earlier.
Okay.
Isn't it nice? It's